Okay, last time we talked about electric distribution. This time let's go back to basics a little bit. Let's talk about electric charge. What is electric charge? So think back to grade school. You had an atom, sort of the model of the atom, right? There's a nucleus. There's things spinning around the nucleus, right? In the nucleus, there is protons, which have a positive charge, right? There's neutrons, which have a negative charge, and spinning around, they sort of describe them as spinning around. I don't know if that's necessarily an accurate model, but spinning around are electrons, which have a negative charge. Cool. So what does charge here mean? So let's talk about let's just pick one of these electrons here and let's talk about it. So an electron, I'm going to draw it over here actually. The way people describe charge, charge has sort of a very generic meaning, but the way people usually, and the way scientists usually describe it, is they describe it in terms of something called a field and an electric field. This is an electric field. And the way you think of it is you sort of have to think of a field like this as a bunch of arrows pointing into the electron. And what does that mean? The arrows pointing into the electron means that anything that has a positive charge, the electron will pull towards it. It's a force, right? Force. This is a force. This is, at the end of the day, like the vast majority of physics is about sort of modeling force. And so this electric field is a way to model and to describe the force of a single electron. So if you have a proton, if there's a proton sitting right here, right? Remember, protons have a positive charge. The electron's going to pull it in. And likewise, if you have an electron here, it's going to be the inverse. The electron doesn't want to pull in another electron. It wants to push it out. So it's a negative sign. So it's going to push out the electron. So it's a way of describing force, and it's a way of describing, it's a property on an elementary particle where that particle is an electron. And it's a property that describes how it's going to interact with other fundamental sort of particles that have charge. So protons have a positive, right? Like a neutron can just go through here. It's not going to impact it. But electron, it's going to repel. So let's describe sort of a simple sort of test problem here. I'm going to clear this thing out. Let's say you've taken, oops, there we go. Let's say you've taken some surface. You've taken like I don't know, a piece of metal or something, and you have just pumped it full of electrons. You've put a lot of electrons in there, like electron, electron. You're just like putting more and more electrons in there. People might describe this as charging the surface, right? So, if you rub your feet on the carpet, or if you take a balloon and rub it in your hair, what you're doing is you're putting a bunch of electrons onto a surface. You're charging this surface, right? Charging this surface. And, you're just pumping it full of electrons, more and more and more electrons. And in fact, if you were to put in 6.24 times 10 to the 18 electrons, which is a really large number, right? Electrons. You would be putting in what's called 1 coulomb, C-O-L-O-U-M-B, I think, 1 coulomb or 1 C of charge. And so this is a really important unit. This unit is really important because it describes sort of a standard set of like how many electrons, how many of these negatively, each one has sort of a charge of -1. How many of these will equal 1 coulomb? And this is the number. It's like it's a huge number, right? But electrons are very, very, very small, right? And so why is this important? This is important because we can now use this to describe potential energy and doing work. And so this is where voltage comes in. And this is sort of like the really important thing to know about voltage. So when people talk about voltage, really you can describe voltage with this. There's one simple equation I sort of like, which is voltage, V, equals J over C. So we know C. So C is like 1 coulomb of charge. And J, and so this is where voltage is super useful, is because this we're talking electricity here. J is joules of work, and which is really cool because this is mechanical work. So for instance, 1 joule, I looked this up on Wikipedia, and this is a random thing, but 1 joule is essentially it has a formal definition, which is kilograms meter squared over seconds squared. But there's a really interesting thing that I thought was really useful to remember. 1 joule is the energy required to lift a tomato. No, this is a formal unit. Lift a tomato 1 meter. 1 meter. Cool. So let's think about this for a second then. So if you have, suppose you've got this, you've created a surface with 1 coulomb of charge, right? Like a balloon. A balloon probably can't hold that much, but you've created a surface with 1 coulomb of charge, right? So you have 1 V equals 1 coulomb of charge, and you and this 1 coulomb of charge can lift a tomato 1 meter, so 1 joule. You have created, this is a representation of what 1 volt is. 1 volt. So voltage, another way to think of this is, do a new slide. Right, so voltage equals, like, 1 volt is equal to 1 joule over 1 coulomb. And another way to think of this is it also has to be measured, right? When we talk about this, it also has to be measured as in a potential difference. So, suppose we have our surface here full of electrons. It's our electron surface. And we've put 1 coulomb of charge in here. 1 coulomb of charge. And we have another surface, which has, say it's neutral, right? So it's 0 coulomb of charge. Right, these electrons are going to want to move this way, right? They're going to want to space out and move into this other side. So when someone's measuring this, you're like, well, how do I think about how to measure this, right? And so you're like, okay, well, I'm going to say this is 0, this is 0 charge over here, this has, this much over here, so this is 1 volt, right? Because this is the potential energy. You have 1 volt, you essentially have 1 joule, 1 coulomb of work to do as these electrons move over. And this is like functionally how a battery works, right? A battery, you have one side of the battery that's full of electrons, and over time, those electrons can move to the other side of the battery, which is either 0 coulombs or has a different sort of representation, or positively charged. You might have positive charges over here. Yeah. So essentially, this is functional. This is functionally called direct current, or DC. So this doesn't have anything to do necessarily with electrical generation or the electrical system yet, but it is important, and it's important to talk about now. So I want to talk about one more thing here. We're going 7 minutes, so let's keep going. I want to talk about one more thing. It's sort of a similar problem. And so we're going to talk about a cloud, and we're going to talk about lightning, right? So lightning happens when you have a cloud, and it builds up a bunch of negatively charges at the bottom. So there's essentially a bunch of electrons. There's a surplus of electrons at the bottom of the cloud. This has to do with heat. I don't know exactly the thermodynamics of why this happens, but you have a cloud, and you end up with the electrons on one sort of side of the cloud, and positive charges at the top of the cloud, and then you might have a ground down here. Here's a person, and maybe you've got like a tower or something right here, right? So what happens down here is the ground is sort of electrically, when people talk about the ground, it's sort of electrically neutral. Maybe it has a small positive charge, but for the most part, it's electrically neutral. So when people talk about a voltage here, they're saying, well, okay, here's all this stuff in the cloud that's negatively charged. It essentially wants to get down here, right? It's attracted to down here. If anything, it has a small positive charge, a huge negative charge. It's attracted to down here. So what happens is lightning happens, right? And so lightning is you're gonna have a big bolt, and what that is the electrons trying to move to the ground. And what's interesting is it's not like all of the electrons just immediately dump at the ground. What happens is they all move a little bit. It's a small number. They'll only move like a tiny amount. But what they're doing is they're pushing all of the electrons in the gas, in the air, down further. And so they're just shoving tons and tons of electrons down into the earth here. And as that happens, it creates a ton of friction, and it heats up the gas. And so the gas gets super hot, right? Hot. And when you think about what thunder is, thunder is essentially a sound, right? So if you're over here, you'll see the light first, right? Light. from the heating of the gas, and then you'll hear it, right? And so the sound is created from sort of the like super quick expansion, and it creates a shock wave. And the light is created by the electromagnetic waves given off from superheating these gases. And so we'll talk about that. And so one thing and the one reason I want to talk about this is moving charges do weird things. Moving charges do weird things. This is like not talked about enough, and how sort of weird and unusual, and how you know, how how strange some of this behavior is, right? So here what's happening is it's heating up the gas, and the electrons themselves are actually moving very slow through the lightning. They're moving, you know, this one particular electron may just move a tiny, tiny bit. He's not going to go all the way to the ground, but it creates a voltage force, right? And the voltage is, you essentially have 0 volts here, and then up here you're going to have something like 3 million volts or something, or I guess it can go up to 300 million volts. And so you've got a huge voltage differential, and when you have that huge voltage differential, it's going to come down to the Earth, and it's going to push down through the gas, and that's functionally what lightning is. Okay, so this is not my best lecture, but the highlight I want to take home is moving charges do weird things. I'm going to make another slide on this because we're going to put all this together. So we've been talking in this one about direct current, in the previous one about alternating current, and then we are going to go from there.